This is a setup for interferometry. I have the oscillators I used in previous videos. This is the very good one, and this is the one that is not quite as good. I have added a notch at 50 kHz below to make the signal very clean at that frequency. Then there is a delay line, so 270 degrees, because the output impedance of this notch needs that cable to be a very high impedance at this point. And then there is a selective load on 9.95, makes the impedance looking this way, precisely 50 ohms at 10 megahertz and also at 9.95. But at 9.95 one looks into the resistor in here. And at 10 megahertz one looks into the output impedance of the oscillator. Then there is a 20 dB coupler, so I can inject a signal from a signal generator. And then there is a second coupler, so I can look at the signals going through here with a spectrum analyzer. Then the signal is split into two equal parts. One goes to a mixer. I'm using the box I used previously for audio, but there is no DC on it, so the amplifiers are not operating. So it's just the Schottky diode output that goes into a varicap that I have put into this oscillator. Half of the power from this oscillator goes from the hybrid into an attenuator and a phase adjust thing with some capacitors and inductors, and then into a hybrid where it is summed with the signal from this oscillator, which was split with this hybrid. So here is the sum of two signals, and I can set the amplitude and phase, so these two signals cancel, or almost cancel, and the output here is low pass filtered. The filter is at this point because there are overtones generated by the mixers, this mixer and by that mixer that is used for the phase locked loop. So the low pass filter removes the problems from the mixer as well as the overtones that come from the oscillators themselves. Then I have a coupler, so I can look with an oscilloscope. And then there is an impedance matching unit, followed by a stepped attenuator and a low noise amplifier, and finally a Perseus. The first adjustment to do on this thing is to adjust the impedance here, so the LNA will look into exactly the same impedance when this is set to 0 and when it is set to 10 dB attenuation. And the reason for that is that the LNA looking into exactly the same impedance will then have exactly the same gain. So the noise floor will not change because of changing impedance. It will just change because of different noise temperature on what the LNA is looking into. And here is the entire arrangement. And you might recognize some of these parts from previous videos. All the way to the big oscillator, the smaller oscillator, selective notch, and so on. Here is the impedance when the attenuator that sets the impedance for the low noise amplifier, when that attenuator is set to 0. And you can see it says 51.5 and 8 nanohenries. And I add 10 dB of attenuation. And as you can see, the impedance is almost exactly the same. And I switch on the signal generator here. And then I get the signal and I compare the levels. This one is plus 0.2 dBm. And the signal I have injected is minus 60.4. So it should be a little bit stronger. Well, like this. So the signal is 60 decibels weaker. And here is what I see on the Perseus screen. 10 megahertz and this signal that is 60 decibels weaker. And I have calibrated for the S-meter to show minus 60 below carrier, it means here. And I switch off the oscillator. And here comes the noise floor. And this is the oscilloscope. I will try to adjust the phase. Like that. And you can see it has some impact on all the spurs. But it doesn't change the noise floor, as you can see, or very marginally. So I wait for a little while and read the noise floor here. Minus 147.5. And now I add the 10 dB attenuation. And we can see the noise is a little bit weaker, but not much. So it is now minus 147, well, minus 148.0. The difference I see is 0.45 dB. That's a factor of 1.0105. This means that the sideband noise should be about 100 times below the noise floor I see. The noise floor at minus 148. So that means minus 168. And this is in a bandwidth of 1 kilohertz. So in 1 hertz, that should be 198 dBc per hertz. Now, this isn't very accurate because the precision here is limited. But this is similar to what I have seen using the notch filter at this frequency. So things are consistent, and what I'm seeing here is the noise of this oscillator, because the noise from this one does not contribute, because on this particular frequency I have removed it with that notch filter. I have removed the notch filter and selective load and send the signal from this oscillator directly into the coupler and the next coupler and further. That eliminated some attenuation, so the signal is now a little bit stronger. So I have to adjust the signal generator to be 59.4 approximately. And that's where it is. So that means that the signal is a little bit stronger. I have to change the calibration. Like this. And I switch off the oscillator. And here is the noise floor without the notch. It means it's the noise generated by this oscillator mainly. And it comes at minus 146.2. Once again, 146.2. And I step in 10 dB of attenuation. And the noise floor is clearly lower. Now it is minus 147.96. And it is of course appropriate to check the impedance. So this is with no attenuation. And here is 10 dB of attenuation. And you can see the scale is very expanded, so each line, I mean, it's 1 ohm from 50 ohms here. And the difference between the two steps positions on the attenuator is in the order of 0.1 ohm or maybe less. So 1.77 dB in difference is 1.04. So 0.04, that is the fraction added. That's 4% or 1 in 25. So we have 14 decibels. Below minus 147, or well, below minus 148. So 148 minus 148 minus 14 minus 30, that's for the bandwidth, comes out as minus 192 dBc per hertz. This seems a little bit too good, but on the other hand, there is no noise from the Schottky mixers anymore. I will now look 10 kilohertz below the carrier. I have to adjust the impedance. It has changed. This is without the attenuator. And here is with the attenuator. So I will adjust a little bit. Now the impedance is about right. This is without attenuation, and here is 10 dB attenuation. And it takes some time before the track, but you see it changed by a very small amount. The very small change of the impedance box did not change calibration much. Here again is the noise floor at 10 kHz offset, without any attenuator and with a 10 dB attenuator setting. The result I see with these new numbers after having retuned the matchbox is very different. It's now 2.8 dB, and that leads to a sideband noise of 178, minus 178 dBc per hertz. Now I am 540 hertz below 10 megahertz in a bandwidth of 20 hertz. And here I look at the noise floor and find this number, minus 154. And I switch in 10 dB of attenuation. And the noise drops by nearly 10 dB. 10 dB more, and the noise drops significantly. So here I do not have to subtract uncertain noise floor levels. This is the observed noise level directly from the interferometry. So what I observe is 154, and then 20 Hertz, that is 13 decibels. And that sums up to minus 167 dBc per Hertz at 540 Hertz. So compared to previous measurements, this black curve, that was with the Schottky mixers. Probably this new very good value isn't quite realistic, but that it is better than the Schottky, that is obvious, because it's clear that the Schottky diodes do contribute with noise. And the other results are pretty close. This exactly on the spot. This 4 decibels too good. And I don't know which one, but 2 dB error on each measurement in opposite directions is not very unlikely. For closer frequency separations, I need a better PLL, because it drifts away too quickly, as it is now. So the sideband noise of the perceivers comes into play easily. So I will do some improvements on the system and see what comes out.